In AI RAN, powered by super adaptive AI, 5G massive MIMO can serve many UEs simultaneously. Conventional AI beamforming trained on large-scale data can greatly improve interference mitigation and energy efficiency. Despite its advantages, AI beamforming struggles under anomalous network conditions, where short disconnections or external interferers can sharply degrade performance. To address this problem, we use Viavi's TerraVM AIRSG to simulate these conditions, and we propose an LLM-based beamforming approach to handle them. AIRSG has a special capability to simulate such anomalies, so we conducted experiments assuming these conditions. To handle these conditions, our LLM-based beamforming uses situation-specific prompting. When UE reports are delayed or missing due to a short disconnection, the LLM guides the model to infer the UE state from recent history. And when the network is anomalous, the model receives natural language input indicating that the current situation is an anomaly. Using scenario data from AIRSG, we apply in-context learning by constructing a prompt from guidance and recent network observations. The LLM can interpret this context without requiring any model updates and generate robust beamforming actions for the base stations to mitigate anomalies. However, LLM inference introduces additional delay, limiting real-time beamforming. To compensate for the LM inference delay, unlike conventional reactive AI beamforming, we exploit LLM's time series prediction capability to enable predictive beamforming. First, it predicts the UE's next location one step ahead. Next, it optimizes beam angles for both base stations toward that predicted position. As the UE keeps moving, it repeats the one step ahead prediction. With this approach, we achieve seamless and robust beamforming under anomalous network conditions. Although anomalies incur energy overhead, the throughput gain is larger. As a result, our LLM-based beamforming increases downlink throughput and improves energy efficiency. This is the structure of conventional AI beamforming based on AI-REC. Based on the resulting UE mobility patterns, the AI model immediately sends beamforming actions to the base stations. But in real networks, data is often missing and delayed. This can happen due to handovers, Wi-Fi offloading, or short disconnections. Also, anomalies can temporarily reduce throughput for reasons that are not captured in CSI, such as external interference or environmental changes. As a result, conventional AI beamforming may rely on inconsistent observations. This can lead to unstable, suboptimal decisions and overall performance degradation. This is the architecture of our LLM-based AI-REC. UE and cell reports stream into the AI-REC to build the LLM prompt and generate beamforming actions for both base stations. We combine two sources of context: offline pre-labeled guidance and online contextual updates from recent network reports. These are embedded into the prompt, enabling in-context learning, adapting via prompt context rather than retraining. The prompt then applies scenario-specific rules for anomalies. This keeps control robust under an anomalies. Now we move to experimental results. Under AIRSG's high-fidelity RAN scenario emulation, we evaluate how the AI-REC performs under realistic imperfect RAN observations. The focus is on throughput, robustness, and energy impact. This graph shows downlink throughput under irregular UE report timing. In the regular region, throughput remains stable. In the irregularity region, the LLM remains robust by using recent context rather than perfect timing. Now we evaluate throughput under a regional anomaly scenario. Even when performance dips, the LLM degrades less and recovers more consistently. This shows stronger robustness under abnormal radio conditions. Beyond raw throughput, we evaluate robustness under anomalies. Robustness is defined as the throughput in each region, normalized by the highest throughput in the normal region. In this case, LLM still improves robustness of beam decisions. Here we show inference time per decision. Because LLM inference can be slower than conventional controllers, purely reactive control may miss the timing budget. This is where predictive beamforming provides a practical advantage, by generating the next decision in advance so it can be applied on time. Next is energy efficiency, defined as downlink throughput over total power. To mitigate anomalous conditions, our proposed LLM-based AI beamforming may consume slightly more energy. However, because it sustains a larger throughput gain, the overall energy efficiency improves. To summarize, we use two metrics: robustness and energy efficiency. Under irregular UE report timing, LLM-based AI beamforming delivers clear gains in both robustness and energy efficiency. Under network anomaly, LLM-based AI beamforming remains more reliable as well. It improves both robustness and energy efficiency, even under localized degradation. Bringing everything together, the goal is operationally robust beamforming under real network dynamics. We conclude with LLM-based context-aware beamforming that improves robustness through mobility-aware interference mitigation, while maintaining energy-aware control.